Welcome to Organic Chemistry. In this video, we will focus on enols, enolates, and enamines. Let's get started. One of the most powerful ideas in carbonyl chemistry is how to control the reactivity at the alpha carbon. Carbonyl carbons have a special feature. The hydrogen atoms next to the carbonyl, the alpha hydrogens, are unusually acidic. When those hydrogens are removed, we generate enolates. And enolates are incredibly useful because they are nucleophiles at carbon. This means we can use them to form new carbon-carbon bonds. But there's a problem. Once you start generating enolates, a lot of reactions become possible. Aldol reactions, Claisen condensations, α-Alkylations, reactions with enamines. The challenge is not whether these reactions occur, the challenge is how to control them. So, we begin with the foundation, enolate formation. When a base removes an alpha hydrogen from a carbonyl compound, the electrons can delocalize. The negative charge is shared between the alpha carbon and the carbonyl oxygen. This resonance stabilization is what makes these protons acidic, but the acidity varies dramatically depending upon the functional group. For example, aldehydes and ketones have pKa values around 17 to 20, while esters are less acidic and amides are even less. The key idea is that resonance stabilization and inductive effects determine how stable the resulting enolate will be. More stabilization means a lower pKa and easier enolate formation. Another important concept is position notation. The carbon next to the carbonyl is the alpha carbon, then beta, gamma, and so on. This nomenclature lets us precisely describe where reactions occur. Now let's begin with acid-catalyzed aldol condensation. Under acidic conditions, we first protonate the carbonyl oxygen. This increases the electrophilicity of the carbonyl carbon. Next, a neighboring alpha hydrogen is removed, forming the enol. Notice that under acidic conditions, we form enols, not enolates. Enols are weaker nucleophiles. But that's actually helpful because it reduces unwanted side reactions. The enol now attacks another carbonyl carbon, forming the new carbon-carbon bond. After proton transfers, we generate the beta-hydroxycarbonyl, commonly called the Aldol product. But the reaction does not stop there. When the mixture is heated, water is eliminated, forming a conjugated alpha-beta unsaturated carbonyl compound. This dehydration step is typically E1-like because protonation of the hydroxyl group allows water to leave. The result is a conjugated pi system, which is thermodynamically favored. But under basic conditions, the mechanism changes completely. Instead of forming an enol, the base removes the alpha hydrogen to form an enolate directly. This is base-catalyzed aldol condensation. Enolates are much stronger nucleophiles than enols. The enolate attacks another carbonyl compound, producing an alkoxide intermediate. Protonation of that alkoxide gives the familiar beta-hydroxycarbonyl. But again, if heat is applied, dehydration occurs. In basic conditions, This elimination proceeds through an E1CB mechanism. That means the base removes an alpha hydrogen, forming an enolate intermediate, which then eliminates hydroxide. This produces the conjugated alpha beta unsaturated carbonyl product. Yet now we move to Claisen condensation, closely related to the Aldol condensation reaction. But instead of aldehydes or ketones reacting with each other, the Claisen condensation involves esters. The base removes the alpha hydrogen from an ester to form an ester enolate. That enolate attacks another ester molecule, and this forms a tetrahedral intermediate that collapses and ejects an alkoxide leaving group. That product is a beta keto ester. One important rule here is that the base used must match the alkoxy group of the ester. Otherwise, transesterification will occur. Another important feature is that the product has very acidic alpha hydrogens, so it is often deprotonated again during the reaction. That's why an acid workup step is required at the end. But now we look at direct alpha alkylation using enolates. Here, we intentionally generate an enolate and allow it to react with an alkyl halide. A very common base used for this is LDA, lithium diisopropyl amide. LDA is extremely strong, extremely bulky, and typically used at negative 78 degrees Celsius. At these low temperatures, LDA removes the least hindered alpha hydrogen, forming what is called the kinetic enolate. Once the enolate forms, it reacts with an alkyl halide through an SN2 reaction, creating a new carbon-carbon bond. One additional detail is that enolates don't exist as isolated ions. They form aggregates coordinated with lithium and solvent molecules. These structural details can influence selectivity. But another powerful strategy for α-Alkylation uses enamines, known as the Stork-enamine reaction. Secondary amines react with carbonyl compounds to form enamines. These enamines behave like neutral equivalents of enolates. The enamine attacks an alkyl halide, forming an iminium ion intermediate. Finally, hydrolysis regenerates the carbonyl compound and releases the amine. This strategy has several advantages. These are under milder conditions, and there are fewer side reactions, and therefore there is much better control over selectivity. That's why the Stork reaction became an important tool for organic synthesis. At this point, we've seen now several reactions that rely on alpha carbon nucleophilicity. The real challenge is controlling which reaction happens when. There are several strategies chemists use. First, intramolecular reactions are often strongly favored because they are entropically advantageous. Second, we can form the enolate before introducing other reagents, which gives strong control over selectivity. Third, enamines can be used to provide controlled reactivity without using strong bases. Fourth, using non-enolizable partners can prevent unwanted side reactions. And finally, we can totally exploit the law of mass action, what you have probably referred to as Le Chatelier's principle, by using one reactant in large excess. Each of these strategies allow chemists to steer reactions toward the desired product. So the central idea of this entire unit is simple but powerful. Carbonyl compounds allow us to activate the alpha carbon, and once activated, that carbon becomes a nucleophile, capable of forming new carbon-to-carbon bonds. Through Aldol reactions, Claisen condensations, Enolate alkylations, and Enamine chemistry, we gain an enormous toolbox for building molecular complexity. The true skill in organic synthesis is not simply knowing the reactions, but knowing how to control them. And that control comes from understanding acid-base chemistry, resonance stabilization, kinetic versus thermodynamic control, and reaction conditions. Master those principles and you unlock a huge portion of carbonyl chemistry. Till next time, Crip.